In this video, we will look into dialysis machines. Let's start the video from the beginning of the dialysis machine. The history of dialysis dates back to the 1940s. The first type of dialyzer, then called the artificial kidney, was built in 1943 by Dutch physician Willem Kolff. Kolff had first gotten the idea of developing a machine to clean the blood after watching a patient suffer from kidney failure. When his invention was completed, he attempted to treat over a dozen patients with acute kidney failure over the next 2 years. Although only one treatment turned out successful, he continued to experiment in improving his design. Kolff came to the United States in the late 1940s and went to work at Mount Sinai Hospital, trying to get kidney treatment to become a health service. Because of the hospital's opposition to the type of therapy at the time, he and his colleagues conducted treatment issues at a separate site. More experimentation led to the manufacturing of an improved design in the early 1950s. However, Kolff's device only treated acute kidney failure and not end-stage renal disease, or ESRD. How the dialysis machine works. The dialysis machine draws up and warms purified water to physiological temperatures. The heated water then undergoes desertion under vacuum to prevent dissolved air from coming out of solution as negative pressure is applied during dialysis. Air bubbles in the dialysate cause the blood leak detector and the conductivity detector to malfunction. They also lock part of the dialysate pathway, increasing channeling and masking parts of the membrane surface area. The heated and deaerated product water is then mixed with the concentrate to produce dialysate. To ensure proper proportioning, the conductivity monitor downstream from the proportioning pump continuously measures the electrical conductivity of the product solution. Because malproportioned dialysate may cause severe electrolyte disturbances in the patient leading to death, the conductivity monitor has a narrow range of tolerance and is usually redundant. Dialysate conductivity may be altered by temperature, the presence of air bubbles, or malfunction of the sensor, usually an electrode. Periodically, the conductivity monitor must be calibrated using standardized solutions or by laboratory measurements of electrolytes in the dialysate. Let's learn about the components of dialysis machines. Single-patient hemodialysis systems can be divided into 3 major components: the dialysate delivery system, the extracorporeal blood delivery circuit, and the dialyzer. Each system has its own monitoring and control circuits. The delivery system prepares dialysate, a solution of purified water with an electrolyte composition similar to that of blood, and delivers it to the dialyzer. The external blood delivery system, extracorporeal blood circuit, creates a portion of the patient's blood through the dialyzer and returns it to the patient. The dialyzer is a disposable component in which solute exchange or clearance takes place. The temperature monitor within the dialysate circuit sets off an alarm if the dialysate temperature is outside the limits of 36 to 42 degrees Celsius, and dialysate is pumped directly to the drain, automatically bypassing the dialyzer. Located downstream from the dialyzer, the dialysate pump controls dialysate flow and generates negative dialysate pressure. The dialysate circuit must be able to generate both negative and positive dialysate pressures within the dialyzer because, although many dialyzers require a negative dialysate pressure for filtration, dialyzers with high KUF or conditions that increase pressure in the blood, or conditions that increase pressure in the blood compartment require a positive dialysate pressure to limit filtration. The dialysate circuitry controls the pressure by variably constricting the dialysate outflow tubing while maintaining a constant flow rate. The dialysate delivery system also monitors the filtration rate, either indirectly by controlling the TMP, pressure-controlled ultrafiltration, or directly by controlling the actual filtration, volume-controlled ultrafiltration. Earlier dialysate delivery systems used pressure-controlled filtration, requiring dialysis personnel to calculate the TMP, enter the TMP into the machine, closely monitor the filtration rate, and recalculate and adjust the TMP as needed. To prevent excessive fluid removal when using dialyzers with KUF greater than 6 milliliters per H per mmHg, dialysate delivery systems capable of performing volume-controlled filtration are mandatory. Such systems have built-in balance chambers and servo mechanisms that accurately control the volume of fluid removed during dialysis once the desired goal is set. Let's learn about types of dialysis machines. First is the conventional dialysis machine, which are used in hospitals or dialysis centers in a conventional standard process. These machines are heavy, bulky, and not a cost-effective equipment. They also require standalone, separate RO systems for assisting the machine. Second is the portable dialysis machine. This type of machine can be used at home or small clinics. A company called NX Stage System 1 is the first and only truly portable hemodialysis system cleared for home use in the United States, including solo hemodialysis during waking hours and nocturnal hemodialysis while both the patient and care partner sleep. It was specifically designed for patients to use in their homes and is small enough to allow patients to travel and bring their treatment supplies with them. And the third type of dialysis machine is the Vicenza wearable artificial kidney for peritoneal dialysis developed by AWAC Technologies, is a miniaturized system for continuous flow PD with capacity to regenerate spent dialysate. Its weight is just about 2 pounds or 1 kilogram. It's small in size and battery operated to provide effective recirculation of PD solution at a rate of 20 milliliters per minute for more than 12 hours. The system is meant to be an alternative for continuous ambulatory peritoneal dialysis, or CAPD, and automated peritoneal dialysis, or APD, to reduce the time consumption, the steps of procedure, and amount of solution required to perform PD. The system is based on a combination of a long overnight dwell exchange and a continuous flow PD during the day, performed with a special catheter and a special mini-cycler which utilized a mixture of sorbents to regenerate the PD solution. There is another type of dialysis machine which is also known as CRRT machine. Continuous renal replacement therapy is a special type of dialysis that we do for unstable patients in the ICU whose bodies cannot tolerate regular dialysis. It is a very different type of dialysis from the routine type that patients may be familiar with, and it requires special skills and expertise. Regular hemodialysis is meant to be mostly an outpatient procedure. It is done usually 3 times a week for 3 to 4 hours at a time. The flow rates used to clear waste products and remove fluid from the patient are very fast, potentially putting stress on a patient's heart and blood pressure. If a patient already has a low or unstable blood pressure or has heart issues, he or she will not tolerate regular dialysis. CRRT is a slower type of dialysis that puts less stress on the heart. Instead of doing it over 4 hours, CRRT is done 24 hours a day to slowly and continuously clean out waste products and fluid from the patient. It requires special anticoagulation to keep the dialysis circuit from clotting. This was the simplified video on dialysis machines. We hope you liked this video, and if you did like it, hit that like button and subscribe to the channel. We'll see you guys in the next video.